Hi, my name is Justin Quackenbush, and today I'm going to be discussing the four fundamental forces. We begin by defining force. Force is the push or pull interaction experienced by objects that would cause movement if left unhindered. All of the forces that will be discussed today will involve some aspect of a push or a pull. In the real world, there is almost never a single force working on a given object at any one time. Different forces can all act upon an object at the same time, and the resulting force will be a mixture of all of those forces. Forces working on an object can be additive or subtractive. The resulting overall force, with its direction and magnitude, depends on the individual directions and magnitudes of the forces applied to that object. This resulting force is called the net force. Newton's third law states that for every action there is an equal and opposite reaction. Therefore, if one object is exerting a force on another object, the second object will exert a force of the same magnitude on the first object. We see force in instances such as tug of war, baseball, and even cars on a road. Here are some common examples of forces. A car crash, a fighter jet, and even an atomic bomb are all examples of forces that we experience here on this planet. These are common forces and their mathematical formulas to solve them. You've likely seen many of these before. All of these different force equations fall into one of the four force categories. Starting from the strongest to weakest, we have the four fundamental forces in the universe. First is the strong force, then the electromagnetic force, then the weak interaction force, and then gravity. Every force that exists in the universe falls into one of these four categories, so it's super important to understand how each of these force categories function. These forces allow for life as we know it, and without these forces, we could not exist. The strong force. The strong force is the push or pull interaction between subatomic particles that holds atoms together. It only works effectively at subatomic particles within very small distances as such. But weren't we taught in all of our classes growing up that protons are supposed to repel each other? This is the schematic of a given atom. And we know that in the nucleus of an atom, we're supposed to have positively charged protons and neutrally charged neutrons. But given what we know about force, aren't protons supposed to repel each other? Therefore, how would atoms be held together? The answer is that the strong force keeps them there. And this stops atoms from falling apart, which is super helpful to life. The strong force holds protons and neutrons together in atomic nuclei by holding together component quarks of each particle. Quarks are the most fundamental particles of the universe. They form the basis of protons and neutrons. There are 6 types of quarks. Scientists refer to each type as a different flavor, kind of like different flavors of juice boxes. As shown in the graphic, there are the up quark, down quark, strange quark, charm quark, bottom quark, and top quark. There is also the theory of quantum chromodynamics, which says that any of the aforementioned 6 flavors of quarks can have one of 3 colors. In a proton or neutron, there must be a red, blue, and green quark at all times. These quarks interconvert, so as one quark changes colors, another quark must also change colors in order to maintain balance of one of each of the 3 colors, red, blue, and green. This interconversion allows protons to remain close together in the nucleus of an atom. The electromagnetic force is our next strongest force. Common examples include electric cars. There are many electric cars that are currently in production, and they use electromagnetic forces to help run them. Examples include the Nissan Leaf, the Toyota Prius, and others. Electromagnetic forces can also help you heat your food in microwaves. Super important for college students. Vision is also the result of interpreting electromagnetic waves, or light. The next force, the electromagnetic force, is made up of two categories, the electrostatic force and the magnetic force. The electrostatic force is the push or pull between two charged objects at rest, and the magnetic force is the push or pull between two charged objects in motions. Electro plus magnetic gives us the electromagnetic force. There are many applications of the electrostatic portion of the electromagnetic force, which we will talk about first. In this first picture, we have multiple point charges and their interactions. Point charges are considered static or unmoving. The push or pull force between these charged particles can cause movement, and that's electrostatic force. We see, as stated earlier, that like repels like, while opposite charges attract. Point charges create electric fields around them. Positive point charges create fields that move outwards, and negative point charges create fields that move inwards. This third graphic shows the Coulomb's force equation for electrical force exhibited in a system with 2 point charges. This was shown earlier as one of the many common equations for force, where K equals Coulomb's constant, Q1 and Q2 are the 2 point charges, and R is the distance between those point charges. Another example of the electromagnetic force is in parallel plate conductors, which cause electric fields from the positive plate to the negative plate. These electric fields leave and enter at 90-degree angles from the plates, and this causes a voltage change, or a voltage drop, between the two plates. This produces a current of charge to be initiated, which creates power. Now on to magnetic applications of the electromagnetic force. This first picture shows a bar magnet, where magnetic field lines move from north to south. Like parallel plate conductors and field lines, the field lines exit and enter the surface at 90-degree angles. This second picture shows that a current through a straight wire causes an induced circular magnetic field as shown. It is in that clockwise direction because of the right hand rule, where the thumb goes in the direction of the current and the fingers curl around in the direction of the magnetic field. This next formula describes the magnetic force on a wire carrying a current, where I is the current in amps, L is the length of the wire in meters, B is the magnetic field produced in Tesla, and theta is the angle between the wire and the magnetic field, which is allowed to rotate. This third picture shows our last example of the magnetic force, where we show a proton moving through a magnetic field, where this magnetic field exerts an electromagnetic force on the proton, which can help to determine the overall direction that that proton will move, as influenced by being within that magnetic field. These next two pictures show that the electrostatic force and the magnetic force are actually the same force, where we can look at magnets as having north or south ends, but we can also look at them as having positive or negative ends, where the magnetic and the electrostatic force are actually producing the same effect. Now, there are the Faraday and Maxwell equations that show that a changing electric field produces a changing magnetic field, and vice versa, where a changing magnetic field produces a changing electric field. This concept helps to explain light, which is just magnetic and electric fields propagating together at the speed of light. And this is how we see. These waves contact our eyes, are focused by our lens, and picked up by our retina. This affects sodium channels in our eyes, which causes an electric potential difference across the cell membrane of retinal cells. This sends an action potential, which is propagated through our central nervous system, eventually traveling to our brain, which receives that action potential and interprets it as sight. Without the electromagnetic force, we would not be able to see. The next force that we're going to talk about today is the weak interaction force. The weak interaction force allows us to do some pretty cool things, such as carbon dating. Using carbon dating, we can determine the age of different organic materials, such as mummies or even fossils. The weak interaction is the push or pull interaction between subatomic particles that is responsible for radioactive decay, the most common type being beta decay. Like the strong force, the weak force only acts at very small distances. Beta decay is when a neutron turns into a proton and emits a beta particle, which is basically just a high-powered electron. This next image shows a schematic of what alpha and beta decay look like in graphical form, where the x-axis shows the atomic number and the y-axis shows the number of neutrons present in any given molecule. So, during beta decay, the mass number remains unchanged, meaning the same number of protons and neutrons are present, but the atomic number increases by 1, meaning there's one more proton, whereas an electron is emitted. This information is placed into context with the help of this last picture. So during beta decay, Z increases by 1, while A remains unchanged because N decreased while Z increased. X describes any of the elements in the picture to the right that are capable of undergoing beta decay, which usually involves transition metals that are large enough to compensate and minimize the effects of changing atomic structure. So how does the weak interaction work? The weak interaction involves the push and pull of quarks and force carriers to convert neutrons into protons. Protons are composed of 2 up quarks and 1 down quark, whereas neutrons are composed of 1 up quark and 2 down quarks. This is described in the following image. The weak interaction is accomplished with the help of force carriers, such as W boson and Z boson. They help a down quark transition into an up quark, allowing a neutron to change into a proton and a beta particle to be emitted. As shown here, this is the process by which we are allowed to use carbon dating, where we can look at any organic material and based off of how much it is decomposed, we can estimate the time frame from when it was first created or since it has perished. Next force that we're going to talk about, and the final force of today, is the force of gravity. Gravity is the pull interaction between 2 objects at mass. It does not exhibit a push force, but is rather always attractive between objects. It doesn't matter how large or how small either of the 2 objects are, there will always be a gravitational force pulling between them. So, right now, there is a paper clip on the other side of BYU campus that's pulling on you, and that you are pulling on it. You might not feel it because you're far away, and you both have relatively small masses, but the gravitational force is there. Gravity is super important. It keeps us rooted to the ground. It keeps the Earth rotating around the sun so it doesn't drift off into the cold universe. And it also keeps the moon rotating around the Earth, which causes waves on the beach and seasonal weather patterns. Why does gravity exist? Isaac Newton attempted to describe gravity by giving us our basic definition of physical gravity, that objects with masses attract each other. However, it was Albert Einstein, yes, this guy, that described how gravity works using his theory of general relativity. He taught that gravity results from the warping of space-time due to uneven conglomeration of masses throughout the universe. This would explain Newton's definition, how objects with masses can interact depending on the size of their masses and the distance between them. In all, in the universe, there are 4 fundamental forces, and any force that you can think of will fit into one of these 4 categories. We have the strong force, the electromagnetic force, the weak force, and gravity. Each of these forces help the universe to function and allow us to live and breathe and interact with our environment. The strong force holds atoms together, while the electromagnetic force helps power electric motors, gives us the ability to see. The weak force is exhibited by radioactive decay and allows us to use carbon dating to estimate the lifespan of organic objects, while gravity keeps us rooted to the ground and the Earth in the perfect position to allow us to continue to live. So that's your 4 fundamental forces. Thanks for watching.